Turn it on, it's on.
Starts with the sound.
Turn it.
Friends, it's my extreme privilege today to introduce the speaker of this HyPhI colloquium, Professor Chandrashekhar Joshi. Normally, I would have tried to do this without a paper, but there are enough key elements that I can't miss, and so that I'm actually using a written introduction about Professor Joshi. Professor Joshi is recognized as the father of experimental field in terms of laser plasma accelerator or plasma accelerators in general. And he has done pioneering work which has completely changed the field. Just to give you an example, a GeV accelerator takes something like a kilometer length of acceleration column per GeV. He has taken a 7 GeV beam and converted it to 14 GeV beam in matter of 1 meter length of column by this technology or methodology or science that he has invented called Wakefield accelerators or plasma Wakefield accelerators in this particular case. Of course, then there is also laser plasma Wakefield accelerators that has spawned up. So, and if you look at any of the really frontline labs in North America doing this kind of science, certainly North America, but beyond that also, most likely you're going to find either his student or a postdoc who has been trained from his lab to do this kind of activity. So he's one of the father figures for this field, made many landmark contributions in all the different avatars of the plasma-based accelerators. Now they are being talked about as serious game changers and contenders for many fundamental applications like particle physics. So it's possible that he will initiate the next version of the CERN equivalent of accelerator based on plasma-based techniques. Over the past 4 decades, he and his colleagues have demonstrated nearly every energy gain and accelerating gradient milestone that you can think of, and such as ionization trapping, betatron radiation, refraction of the relativistic plasma beams at plasma boundaries. He, of course, has been honored with a number of awards, and I will tell you only some of the most important ones. The APS DPP Excellence in Plasma Physics Award, Maxwell's Prize in 2006, IEEE Plasma Accelerator Science and Technology Award 2009, Mary Skolodowsky Curie Award and Medal 2017, Lise Meitner Award 2018, and recently the Alfman Prize in 2023 of the EPS. So, of course, he's a fellow of the APS, IEEE, IOP, and elected member of the US National Academy of Engineering. So, it's indeed a great pleasure to have him here at TFR Hyderabad. He visited us in the past in TFR Mumbai, and we told him that there is enough interesting stuff happening in TFR Hyderabad, and it will be a pleasure to have him here. He's taken his really busy time off to be with us for a couple of days. He'll be visiting, of course, our other colleagues in Hyderabad as well. He is a person with really wide spectrum of knowledge from science applications, science policies, and the kind of things that are can make and really develop a nation seriously. So I won't take much more time. I will give him the floor to talk today about the perspective of plasma accelerators. Professor Joshi.
Thank you very much, Ankit. First of all, I'm a teacher at university. And as such, if you don't mind, I prefer to stand here and talk to you guys. And if you feel like I'm not being very clear, don't wait till the end of the talk. Just raise your hand and I'll call on you and we'll just have a talk about it, okay? So what I'm going to talk about is give you a perspective. Hang on, what did I do with a perspective on plasma accelerators? And it's based on an article that I was asked to write during COVID by the Physics of Plasmas, the preeminent plasma physics journal. And they said, well, can you write a perspective article that will tell the readers, what the current state of affairs is in plasma accelerators and what the near-term applications are, because what we're trying to do is build a plasma accelerators for a future linear collider operating at the energy frontier of particle physics. And I'll say something about what that exactly means. Okay. What's shown here is computer simulations. Okay. Computer simulations of acceleration of an electron beam and a positron beam and their collision in a plasma itself. Okay, so it's a new idea for both building a particle accelerator for electrons and positrons and colliding them by focusing them inside a plasma. Everything is done inside a plasma. Okay, now, as you can imagine that this work was started by myself when I went to UCLA as a postdoc. And there I was looking for something new to do. Okay, my advisor, Professor Francis Chen, maybe those of you who are plasma physicists have read his book, okay, said, well, you know, there are any number of things you can do at UCLA. Plasma physics is very big, and don't worry about it. I said, no, I prefer to try to do something new. Okay, and at that time, John Dawson, who was in the physics department, had come up with an idea of a plasma-based accelerator, which was very rudimentary at the time. And I said, you know, maybe I'll see if this idea works. Okay, and that was the genesis of the plasma acceleration group at UCLA. And since then, which was in 1980 around, okay, the group has graduated almost 50 students, and I don't know how many postdocs and researchers, okay, a large number. And these people have gone on to form their own groups, and they've done excellent work. I cannot possibly do justice to all their work because, you know, I'm trying to cover 40 years of work in an hour. Okay, so, but what I do want to say, it is really a work of many hands, done in many places, and I want to really say big thank you to my students and collaborators for all their work. And if I left anybody out, it was unintentional. Okay, what this shows basically is some of, not all of, because this is like 14 years old slide, okay, 10 years old at least, okay. Some of our papers that have appeared on the front page covers of the journals. Okay, so these are not just front page covers in which our papers appeared, but actually our work was featured on the journal because it was the highlight of that issue. Okay, and so I'm very grateful that the journals have also been, and editors of the journals have also been supported. It's a virtual cycle also. I don't claim that all these papers are better than anybody else's work, but it's like a virtual cycle that the journal editors trust you when you write to them saying, this is the most important work in the last 5 years that I've done, and I'm submitting it to your journal. And they believe. Okay, so I'm glad for that. Okay, so what about why do we need particle accelerators? And this slide is really for students. So forgive me for those of you who are more knowledgeable than I am about particle physics or about physics in general. Okay, but the story really begins in 1897 with J.J. Thomson at Cavendish Lab, who discovered the electron using cathode ray tube. You probably all know that, including every student, okay, learns in physics that and how the electron was discovered. He basically applied an electric field and a magnetic field and deflected the electron. And from the deflections, he calculated E to M ratio. Okay, very vaguely. I mean, the actual ratio was measured by Millikan later on in the oil drop experiment, which probably a lot of you probably have also done. Thomson called it the electron, and he proposed the plum pudding model, which you probably also heard of. Okay, plum pudding model of matter. Okay, in which he said the electron charge were distributed as the pudding, okay, or kheer, if you like, okay, and the plums were basically the nuclei. So he understood that there had to be equal charges and matter was charge neutral. He understood that, okay, but it turned out that that model was not right. It stood the test of time for a while, but then it wasn't right, okay. Thereafter, Rutherford came around and he did experiments using alpha particles. So all these discoveries happened in parallel, okay. So basically, Thomson found the electron by ionizing a gas, accelerating the negatively charged lighter particles, and observing them on a fluorescent screen. Okay. Rutherford then used alpha particles because people had discovered radioactivity and they realized that it emitted alpha rays, beta rays, and gamma rays, which were photons basically. Well, alpha rays and beta rays, they knew beta rays were electrons and alpha rays were heavier. He took alpha particles, bombarded gold foils with it, and from the deflections of the alpha particles, and the original experiment you can still see in Cavendish Lab in Cambridge, and there is a replica of it in the British Library Museum. Okay, because that's how important it was. Okay, and he deduced that the nucleus was actually positively charged because it repelled some of the alpha particles, which were also positively charged. Okay, but he realized actually that the positively charged particles themselves, and they were tightly bound, he realized. Most of it was empty space because most of the particles went through. Okay, so he realized that the alpha particle, the protons, we call them protons, the positively charged particles in the nucleus would repel each other. Okay, so there must be, he postulated that nucleus consisted of neutral particles because he deduced that there were equal number of electrons and protons. Okay, but so how were the positively charged particles held together? So he deduced that there must be neutral particles that he didn't call them neutrons, but he deduced that there were neutral particles inside the nucleus. Then 20 years went by, and Chadwick repeated the experiment, except instead of using a gold foil, he used, I think it was either, it wasn't a plastic, the plastic didn't exist. It was candle wax. Okay, very light candle material. And he deduced that he actually discovered the neutron, and he actually called it the neutron. Both of them won the Nobel Prize. So we gone now from 1897 to 1911, which is discovery of the nucleus, and then and discovery of the proton, and then discovery of the neutron, 1932. And by 1932, Thomson declared that all physics was known. Okay, there was nothing to be discovered anymore, and things stayed that way thanks to two world wars that came along. Okay, World War I from 14 to 18, and then World War II, I think 1938 to 45, and that held back. That was golden age for technology because of weaponry, but it held back held back physics. Okay, it was only when towards during the Second World War that Lorentz discovered that particles could be accelerated using RF fields, radio frequency fields, that the age of accelerator-based physics was done. Okay, and he built the first, I'll show you the picture of it, the first accelerator called the cyclotron, which fitted on the palm of his hands. Okay, but he was so confident of the promise of accelerator-based physics that he proclaimed that a new dawn of physics had arrived. Okay, and it is also the dawn of privately funded physics. Okay, because no government agency would fund his work because they were fighting a war. Okay, but there were enough people, enough rich people in California to say, hey, if Professor Lorentz at Berkeley says that, we'll give him money to build bigger and bigger cyclotrons. Okay, so I find that very fascinating. Okay, so as soon as, so the cyclotron energies were increased, eventually cyclotron became synchrotron. I'm not going to waste your time telling the difference between cyclotron and synchrotron. In a synchrotron, the orbit of the particle is kept constant. As the energies increase, you take into account the relativistic increase in the mass of the particle. Okay, and when these particles were bombarded or focused onto a fixed target, okay, all sorts of new particles emerged. Okay, and they were called mesons. Okay, and actually the meson, the first meson, which was well, the pi meson and I don't know, mu meson maybe. Okay, the first mesons were first discovered in cloud chamber experiments because they have a long life and they survive the transport from where they're born. Okay, showers in the atmosphere. Okay, so every time a new particle was found, there was a Nobel Prize in physics. Okay. And there were about, if you look at the handbook of particle physics, there are actually 200 different types of mesons which were found eventually. Okay. People kind of got tired of this. Okay. Not every time a meson was found, you give them a Nobel Prize, was not on. Except apart from the kaon and the pion, all the others were unstable and their lifetime was shorter and shorter. And it wasn't until Murray Gell-Mann at Caltech proposed that all these mesons were formed from quarks. And what were quarks? They were basically one quark and one antiquark held together by a gluon. Okay. And so after he proposed this model, we got the periodic table here, periodic table of nuclear particles, okay, which consisted of basically quarks, which are hadrons, the leptons, which are the electron and the electron neutrino, the muon and the muon neutrino, and the tau particle and tau neutrino. And then the bosons, which is here, is basically the gluon, the photon, which is a carrier of the electromagnetic wave, gluon, the carrier of the strong force, the Z and the W particle, which is carrier of the weak force, and the latest particle on the arrival at the LHC is the Higgs particle, which is the particle that gives all other massive particles the mass. I won't go into how that happens. Okay, let's move on. Okay, so as I explained, the arrival of the high energy accelerator dawned a new era in physics. Okay, and last century was then called the century of physics, largely because it also produced the nuclear bomb, okay, which is not to be forgotten, okay, and enabled, if you like, the good side to win the war. Okay, here is Lawrence with his cyclotron, and this is it. He's actually holding it in his hand. That's how small it was, and he accelerated protons to 70 kilo electron volts. Okay, that's it, 70 keV. That's all the energy was. Here is the state of affairs today, which is portion of the LHC, the Large Hadron Collider at CERN. And it was pleasurable for me when they were building it. And I took the same elevator as described in Angels and Demons. Maybe some of you read the book. Okay. And went down. It hadn't come online yet. And they said, this is the dipole that the Indians made. I was very, very proud that they actually mentioned it. So anyway, it wasn't that dipole. That is a dipole, by the way, dipole magnet. But anyhow, this is a section of the circular collider that has 27 kilometers circumference. And it costs just the cost of building it was $6 billion. The actual cost, if you actually say, how much were people paid? Well, most of the money goes into, in Switzerland, certainly, okay, into salaries. Okay, it costs more than $20 billion to build. Okay, and it is very clear that $20 billion is much too much today. They have proposed to build the FCC, the Future Circular Collider, which will be 100 kilometers in circumference. It will take the LHC as a, if you like, a pre-accelerator to be injected into the main accelerator ring, which will be 100 kilometers in circumference, and God knows how much it will cost. Okay, we really don't know. So it's almost certain that we're not short of space because these accelerators are very deep underground, and you know there's nothing there. You can probably construct a 100-kilometer tunnel, but you'll run out of money before space. No question about it. Okay, I don't think even an international collaboration is going to supply $100 billion, and then of course there's the cost of running the machine. Okay, so this is a problem. All right. Now, so you might ask, well, perhaps accelerator-based physics is over. Let's move on, do something else. Well, so there was a study commissioned, and it's a very interesting book. I urge you to read it. It's called Connecting Quarks to Cosmos. Okay, it is actually a study commissioned by the National Academy of Sciences, and one of the rare studies which are very readable because the leader of the study was not even a physicist. He's an economist from Princeton. Okay. And so he insisted on clarity. And so it is actually very readable. And it starts with what are the most important problems in physical sciences. Physical sciences means physics, chemistry, and geology, I think. Okay. Physics. I forget now which one. What physical sciences constitute. Okay. Naturally, almost the first 10 of the 14 are all physics. Okay. And so I wrote down, I look at it and say, how many of these problems require an accelerator to answer? Well, it turned out, are there additional dimensions of space? Well, it turns out, I'll come on to that, I'll show you. The so-called, let me go back. The standard model of physics, which essentially arranged all these subnuclear particles into a table, is superseded by a new model called, probably you guys know, is called the string theory. And the problem with string theory is it has, the mathematicians think that it has predictions. It makes predictions. It says that particles are not really point-like particles, but they are strings. Some of them say there's not even strings, but they are two-dimensional membranes. Okay. And so they say, well, that's predictable. No, it's not a predictable unless you say, I know, I can predict how you can test it. And there's no testable thing as far as I know. Okay. Well, string theory, one of the great things about string theory is the number of dimensions of space. Well, we all know number of dimensions of space is 3, and the 4th dimension is time, but that's not true. According to string theory, some of them say there are 11 dimensions, some of them say there are 12 dimensions, some of them say there are more than 12 dimensions, 30 dimensions of space. Okay, so, well, can we test more than 3 dimensions of space? Well, perhaps you can, but it turns out the actual energy at which these dimensions become accessible, you might think is very high, but it's not that high. Okay, it is about 300 GeV. Okay, and that is the reason for the electron collider proposed at the FCC. Okay, to look for higher dimensions of space. Then there are supersymmetric particles. For every particle, there is a supersymmetric partner, and so you would think there should be, this is bonanza for scientists, right? But operation of the Large Hadron Collider has yet to uncover any supersymmetric particles. So we don't know. Okay. Okay. Now, another critical problem is, why is there matter-antimatter imbalance? Whenever we collide particles that have sufficient energy, okay, new particles are created from the energy density that is the high energy density that is produced, and equal numbers of matter particles and their counter antimatter particles are produced. For example, okay, if you produce a certain number of electrons in a collision of, just always say, imagine proton-proton collisions at the LHC, then there are equal number of positrons produced. That is how, in fact, positrons are produced. You essentially send a high energy electron beam or a photon beam or a proton beam onto a solid target, and that energy is converted, a fraction of that energy is converted into electrons and positrons. Okay. If you send higher energy proton beam, then you get essentially muons and anti-muons. And that is how, it actually, there's an intermediate step called pions. So the proton energy is converted into pions decay, and into muons and anti-muons and neutrinos. Okay. Okay. Now, so, but if you look at the universe today, we find that almost all the matter that survives is matter. There are no antimatter galaxies, no antimatter, large amount of antimatter. Okay. There are no positron galaxies. Okay. And so, question is, how did this matter-antimatter imbalance come about when, in fact, matter and antimatter must have been produced at the time of presumably the Big Bang, okay, in equal amounts? Then how did the universe begin? Well, this is a philosophical question, really. Okay, whenever we collide beams, we at ever higher energies, we effectively go backwards in time, closer and closer to the beginning of the universe. Well, it's not clear what energy is needed to reach the exact Big Bang. Okay, so it's not infinite, but there's no, but it's very large amount. Even 100 TeV is not accurate. Okay, what is the nature of dark matter? We know that the amount of, this is a relatively new idea. Okay, and it's come about from observations, and we now know that the matter as we know it forms about, I think, 4%, 4.9%. Okay, of the, it says, hang on, see here, atoms basically is about 4.9% of the total matter. Dark matter is 26.8% of the total matter, and the rest is dark energy. Okay, and how do we know it? Is because from the expansion rates of the galaxies. Okay, now we know the amount of matter that galaxies contain, so we know their gravitational attraction or their repulsion. Okay, and they seem to be moving apart from each other at a much higher rate than that. So there must be missing matter. Okay, then how were heavy elements created? We all think that, well, we know that elements like helium came from hydrogen and so on. Fusion created heavier elements. But fusion cannot account for energy, matter heavier than iron, I think. Okay, and therefore, question is, well, we know elements up to now 114 exist. Okay, so how were these elements created? What we tell our children, including me, teaching my son, okay, or trying to get him excited into science, kind of say, well, in supernova explosion, the energy density is so high that you get suddenly fusion of heavier elements is possible. That's not possible. That's not true, right? Because we know how the energy per nucleon, varies the function of Z. Not possible. So question is, how were heavy elements created? And to answer that, we need a collider. And the collider we need is not the kind that is an electron-positron collider, but the Large Hadron Collider can collide heavy ion beams. Okay, so the point is, in the collision of heavy ion beams, can we actually create super heavy nuclei? And in fact, we can. That's how they were created, actually. Okay, we can, but we do not know the details of how they were created. So we have a RIC reactor at Brookhaven, and RIC reactor produces quark gluon plasmas and an enormous number of heavier ions. Okay, but we still do not have a good theory as to how they were created. Okay, let's move on. Okay, so particle colliders in the 21st century. I know I haven't come on to plasma colliders, but I'll move fast. Okay, particle colliders in 21st century. What is the state of affairs today? State of affairs today is that two new colliders have been proposed. The first one is called the International Linear Collider. Okay, here it is. International collides electrons with positrons. So this, for example, collides electrons with positrons. So this, for example, is the electron arm. Okay, it's the electron source. It accelerates the electrons. Okay, some of them are deflected. They hit a solid target, produce positrons. They're collected and they are brought back here. So actually, in this case, they go here, and they are accelerated in a positron accelerator. And the positron beam and electron beam are collided at a small angle. I won't explain why that is, all that. That is details. Okay, and you do physics. Okay, so this ILC has not the design energy of 500 GeV, and already at 250 GeV, the cost was $20 billion. Okay, the 500 GeV version was 30 kilometers long because the accelerating gradient in these RF accelerators were 20 mega electron volts per meter, and it cost about $20 billion. This is Department of Energy estimate, and Department of Energy said, okay, we're not going to build it. Okay, and Japan has been the biggest contender. Nobody wants to go to China because hardly anyone can speak Chinese, right? And so apart from the Chinese, so there's no takers essentially. The international community doesn't want to go with China. Okay, So Japan is the most likely candidate. Every year, the Japanese government says that, yes, we'll consider it this year. Year goes by, no decision. And this has been happening for more than 10 years now. So quite possibly, it will not be built. Okay. So actually, as early as in the 1980s, oh, sorry.
Tectonic instability of Japan, why is it even considered as a candidate?
Well, that goes to show that technology, that question is, given that Japan suffers from earthquakes and hurricanes and all these things, okay, why do they even consider Japan? Well, that technology, civil engineers have become very smart, okay? There was a time when every Japanese house had wooden doors and paper screens, right? Okay, not anymore. You go to Tokyo, there are 60-story buildings, right? And they're on a roller and they move with go with the flow with the earthquake. So technology, civil engineering has become so good that they have no problem building a structure underground that will withstand earthquakes. Okay, does that answer your question? Okay. Okay, so it was realized as early as 1980s that there was going to be a crisis in accelerator-based science. Okay, and I like this view graph. Okay, so cavemen come up with the greatest discovery, arguably. Somebody might say sliced bread is the greatest discovery. You know, I mean, you kind of that's laughable, right? But this is perhaps the greatest discovery, a wheel, right? He made a wheel out of stone, and it was the greatest discovery. And so he made a bigger wheel and a bigger wheel. Well, that's great, and perhaps it enabled him to build the pyramids. Okay, move incredibly large stones. Okay, much more easily than carrying them on the back or pulling them or whatever the people did. Okay, but there's a limit to this. You can't keep on just. That's not going to make a difference in ability of the society to move forward. It's fine for the pharaohs, okay, to do this. Okay, so here's the cave woman who's probably starving. She's hoping that he'll come back with some meat, okay, some shikar, and he comes back with a bigger wheel. Okay, she says, yes, but what have you invented lately? Okay, and that was the case. The Department of Energy, which was kept on funding bigger and bigger accelerators, eventually got tired of it, and they said, there must be a better way of doing this. Okay, and so the question was, so they held a conference at Los Alamos, and they said basically something simple. Can electric fields, okay, of laser pulses or particle beam themselves be used to accelerate particles at a very high rate and more efficiently? So high rate meaning faster, not 20 MeV per meter, but 20 GeV per meter, 1,000 times faster, so that accelerator can be made smaller, and high efficiency, meaning it can be made cheaper, because the cost of the electrical cost of running the accelerator is horrendous. Okay. Okay, so in 1980, I went to UCLA. I saw Dawson's paper. I said, maybe I'll do some work. And we did some original work. I'll briefly mention it. And we hadn't accelerated even a single electron. Okay, we had simply shown that it is possible to produce waves in plasmas that were suitable for accelerating electrons. Okay, so at that time, this conference was held at Los Alamos, and in 1982, I got married. Our wedding was in Bangalore, and we went back to United States, and we hadn't even been on a honeymoon. There was a letter waiting for me from Andrew Sessler, who was the director of the Lawrence Berkeley Lab, saying that there's going to be this conference at Los Alamos on laser acceleration particles, and could I come and give a talk, okay, on it? I said, how did he know what I'm doing? I'm a lowly postdoc, And he said, I actually wanted John Dawson to come and give a talk because he had written the original paper. But he said that you know all about it and you've done some experiments. It's nice to hear about experiments. sorry.
Kind of gross.
Can you get mute? Some of the speakers, some of the people there.
Oh, he's hearing there's a echo?
Yeah, please mute if you don't have any question to ask.
Okay, I think is it muted? So was the question or?
No,
Oh, there was a feedback. Okay, sorry. So would I come to Los Alamos and give a talk on this? And I said, sure, but I was just married. I just come back the day I came back. Okay. So I went home and I said, how would you like to go to Los Alamos for honeymoon? And my wife said, is it nice? I said, oh, it's a wonderful place. So off we go to Los Alamos. But it was freezing, absolutely freezing. Okay. Not different than going to Colorado, going to Chile. Okay. It was freezing. I don't know what minus what. Okay. But it was wonderful because I gave a talk, and that was really one of the best things I did because it was the birth of plasma accelerators. Okay. But it turns out that I can't take credit for this, and neither can wakes, acceleration of particles by plasma wakes. Maybe John Dawson can take credit for it. Basically, the fundamental study of wakes goes all the way back to Leonardo da Vinci, possibly the last human being who knew all human knowledge. It is said, right? We can't prove it. Okay, it is proven. There's Leonardo da Vinci. This is his notes on study of wakes, 1509. I only wish that our Mughal emperors or whoever were, ruling at that time had the foresight to spend money on hiring people to do science. Okay, but not to be the case. Here it is, study of wakes. And Leonardo was very conscious of the fact that he was a genius. So he wrote in mirror writing. Okay, so nobody would steal his work. Okay, but you can put it in the mirror and you can read it. This is actually written in Latin. Okay, and he kind of showed that if basically a wake was nothing more, okay, a wake was nothing more than a disturbance produced by an object such as a piston in either piston was moved through the fluid or piston was stationary and fluid was moving past it. Okay, so wake was nothing more than a disturbance. And the question was, can this wake be used to accelerate particles? Well, it turns out in the plasma it can, for the simple reason, in the plasma, if you take a laser pulse, or here, laser pulse, and send it through the plasma, what it does is, as the intensity is increasing, okay, there's a force on the electrons because of the gradient of intensity. So the intensity here is high, here is low, there's a force forward, and here in the back half, the force is backwards. So electrons are pushed forward and backwards. The electrons are not going faster than the speed of light. Okay, the laser is always going faster. Okay, but electrons have been given a forward impulse and backward impulse. Okay, so they move forward and backward, and as the laser pulse goes past it, these electrons snap back because of the ions, which are heavier, and they snap back and oscillate about the ion. And that is the physical reason why this wake comes about. Okay. Oh, sorry. This wake comes out. This is the electric field of the wake. The electric field of the wake comes about because the electrons are displaced from the ions. And the reason why the field is high is because the plasma density is high or the ion density is high, and ion density, electron density is equal. Okay, so because the density is high and the scale lengths are very small, okay, the electric fields are incredibly large. So that is called the laser wake field accelerator, because the laser pulse here is forming a wake field here, wake. Okay. Now you can do this with a particle beam. If you take a charged particle beam, imagine an electron beam, which is highly relativistic. So it's more massive. Each electron looks like a proton, okay, or even heavier than a proton. It's sent through the plasma. Well, these electrons are more massive, but they're negatively charged. So plasma electrons see an excess negative charge. Okay, and they're light. Plasma electrons are light. When this beam that you send through is heavy, so nothing happens to the beam, but plasma electrons just move out of the way. Okay, so they move transversely out of the way, although this is a one-dimensional picture. And as the beam goes through, they snap back about the ion and set up an oscillation. And wake is nothing more than an oscillatory wave produced in a plasma that has an electric field. Okay, let's move on. Okay, now, if you actually, this wake moves at the speed of light because the laser or the electron beam is moving at the speed of light. So it is, and it has a lifetime of picoseconds. Okay, so a structure that is moving at the speed of light, it is micrometers in diameter and 100 microns maybe in length. Okay, and it's moving at the speed of light, and it has a lifetime of a few picoseconds, few trillionth of a second. Okay, so how do you even visualize it? How do you know it happens? Well, people, experimentalists are clever. They designed ways of moving, taking pictures of these wakes that are transient structures in plasmas. And here it is. Okay, here's a picture of a wake, and here's a picture of a slow wave cavity or copper cavity that is used by, in conventional accelerator. And that looks like this. So it really is the same thing. Okay, now it turns out that in a conventional accelerator, you have to use a TM wave because TM wave has a longitudinal electric field that is moving in the same direction as the particles. Okay, and a TM wave, as you all know, I'm sure from electromagnetics classes, has an EZ field, that is field in the direction of propagation. So that's the Z. Okay, ER field, a transverse direction, which focuses the particles and defocuses the particles alternatively, and a B theta field from Ampere's law. Okay, and same thing in the plasma. When electrons are displaced from the ions, there is an EZ field, ER field, and a B theta field. So it really is a TM wave. Okay, an electrostatic wave in a plasma is transverse electromagnetic wave type of structure. Except, as I said, because the scale length is very small, instead of 20 megavolts per meter, at which point you begin to get breakdown of this structure, and this structure is already broken down, that's what a plasma is, the electric field is more like 20 giga-electron volts per meter, 3 orders of magnitude large, and really it had to be 3 orders of magnitude large for a funding agent to say, let's invest in it. If it was factor of 2 large, they said, not interested. If it was factor of 10 large, they would have said not interested. Why? Because an existing technology continues to improve. This is a fact of life, experimental life, okay? And a new technology takes a generation to develop. So if that is true, a generation is 25 years, and in 10 years, technology will improve naturally by a factor of 10, okay, then it's not going to work. Okay, but if it is 3 orders of magnitude better, then there is a chance that the new technology can be developed in time to supersede the existing technology. And this is the principal reason why silicon-based electronics has not been replaced by any other. Although I'm an electrical engineer, I'm from electrical engineering department, gallium arsenide has many advantages. Okay, there are many other types, now graphene transistors have many advantages. Okay, but it's not going to change. We're not going to anytime soon have a laptop made out of gallium arsenide. It's not going to happen because billions of dollars, tens of billions of dollars, God knows how much money has been spent into perfecting silicon-based technology. Same thing with accelerators. Billions of dollars have already been spent into developing RF accelerators. A new technology to come along and replace it, which is going to, the development of it, which is going to take $1 billion or perhaps several $1 billion. Okay, cheaper doesn't mean free. Okay, cheaper means less than it would otherwise cost. Okay, maybe cheaper means it is still affordable for humankind as a whole. It's a grand, at a grand scale, no matter what. Okay, but cheaper does not mean free. Okay. Okay, let's skip the plasma physics part. Okay, so I'll skip this too. Okay. Very quickly, we realized that these wakes had to be in the nonlinear regime. And I'm going to spend a little bit of time explaining what this is. It's called the bubble regime also. And why is that? Because normally, nonlinear plasma physics is a bad word. it is like a curse. Okay, if you say, oh, nonlinear wave in a plasma, that means wave, instead of a sinusoidal oscillation, it has become something different kind of structure, and it's not going to last. It's going to be, it's going to evolve into turbulence. It's going to be horrible. Okay, well, it turns out this is an exception. Okay, because wake turns out to be an impulse response of a plasma to a disturbance, and an impulse response is incredibly reproducible in its frequency content, in its dispersion. You can predict it. Okay, so what is a nonlinear plasma wave? A nonlinear plasma wave is when a very powerful laser beam, here is shown, very powerful laser beam, is sent to a plasma. And I talk a little bit about lasers because you guys are going to have a petawatt laser. And this is what you would have to do if you're interested in particle acceleration. And you can do a lot of things, okay? So an intense laser beam is sent through the plasma. It produces a plasma by blowing out all the electrons, except in the one-dimensional case, I said electrons are pushed forward and backward, but now the transverse gradient of the intensity is also very large, and the electrons are also pushed on the sideways. Okay, they're pushed forward, backward, and on the sideways, okay? And all the electrons are pushed out. Every electron contained in the volume occupied by the laser is pushed out, okay? As the laser moves forward, okay, these electrons come back. That's what's shown here. That's what's shown here by the dotted white line. Oh, they're shown there, dotted white line. Electrons are coming back, and it's called an electron sheath. And inside the electron sheath are only ions, okay, positive ions. And they come back here, they overshoot, and they form essentially a bubble-like structure. Why is it called bubble? Because a bubble has air inside and then a plastic sheath on the outside, right? Okay, so this is called bubble because it's got ions on the inside and electron sheath on the outside. Okay, now, since there are ions on the inside, so they're positively charged, and the electrons on the outside, there's an electric field that goes from positive to negative. So it will be pointing from 0 at the middle, that way and that way. Okay, and so this electric field can accelerate another beam of electrons if you place it at the back. Why? Because force on the electron is minus EE by, okay, so Lorentz force on the electron is minus EE, and it will be pushed forward, and these electrons can gain a lot of energy for a simple reason. The laser is going at the speed of light, the bubble is moving at the speed of light, and the electrons, are moving at some fraction of speed of light, close to speed of light, but not at speed of light. And therefore, it takes them a long time before they start outrunning the bubble. And in the process, they gain energy, they become even more massive and more lethargic as a result. Okay, now you can do it with the electron beam also. You can say take an intense electron beam, blow out all the electrons because it's negative charge, and these electrons come back and they cross here and form a wake. And in the black, I've shown longitudinal electric field inside this bubble, and you can see positive electric field decelerates the drive beam, and negative electric field accelerates the trailing beam. Okay, now from now on, I'm going to talk mostly about waves driven by electron beam, because personally for me, we did first many years, 2 decades of experiment at UCLA using lasers that we had, and we got very far with it. But eventually we realized that high energy accelerator designers were not going to take us seriously unless we showed, energies of interest to them in a distances much shorter than what they could do. Okay, and that means we really had to go to an accelerator to do this. Okay, I'll skip that. Okay, so off we went to SLAC. I remember I went with John Dawson to see Bert Richter, who was a Nobel Prize winner and head of the lab at that time. And, he was kind of mean. Okay, we sat there and he kind of said, what brilliant idea has come out of UCLA lately? And John was so oblivious. He was such a nice man. He was so oblivious. He cheerfully started telling me about wake field acceleration. And he kind of said, well, has this been shown in practice? And I was a lowly person. I wasn't even a faculty member, still a postdoc, more than 2 years now. Okay. And 4 years had gone by. I was still a postdoc. And I said, yes, actually, we've shown it and we've published this in Physics Letter. And said, okay, send me a proposal and I'll run it by the PAC committee. PAC means Program Advisory Committee. Okay. And these were full of all high energy physics. There had never been a plasma experiment done at SLAC. SLAC had won 4 Nobel Prizes by then in particle physics already, including one for Bert Richter himself, okay, who developed for the development of J-psi particle. Okay, so off we went, and it turned out we were very lucky. And this actually, I am a firm believer in serendipity in science. Okay, everything doesn't come because you are brilliant and you thought everything through, because we hadn't thought everything through. We didn't even know what kind of plasma to use, because at home, we could fire a shot once a minute. Okay, and then plasma was an arc discharge plasma. And we went there and they said, I said, well, how often does your accelerator fire? They said, 10 hertz. I said, 10 hertz? At 10 times a second? No plasma source had ever been made that worked at 10 hertz. And that was completely reproducible, homogeneous. Plasma, if you knew its density within factor of 2, you were lucky. Okay? So I said, this is a problem. I said, well, and what would you consider a success? I asked him. He said, one electron, I want to see one electron to accelerate it to 1 GeV in 1 meter. So 111. It's very simple. Okay. I said, that should be possible. Little did I know whether I didn't know whether the plasma source could be made. I didn't know anything. Okay. And it's another story altogether about development of a plasma source. But at UCLA, we went back and made a lithium ion source. Okay. And that lithium ion source has been so successful that it has been used in every successful plasma accelerator experiment with beams, and including those on the Awake experiment. Instead of lithium, they use rubidium, but it's the same idea, basically. Okay, alkali metal source. And it is so uniform that any experimental variations have been ascribed to changes in beam not being reproducible, than plasma not being reproducible. Okay, so it took about several years because we had to learn how accelerators work, how to integrate a plasma source inside an accelerator, inside a slack beam line, which was a 50 GeV accelerator. But 7 years later, here's the result, front cover of Plasma Physical Review Letters, of course. Here's the original beam at 20.5 GeV, electron beam. And here's a beam that went to plasma. And most of the beam, of course, lost energy in producing a wake. And back of the beam was accelerated. So it was just one beam, was accelerated again by about the same amount, about 4 GeV. And it shows basically the original beam in black, 2-horn, double-horn distribution. And here's a beam that has gone through plasma. A lot of the beam has been decelerated, but the back of the beam, or 8% of the particles gained energy by about 2 GeV. So this broke the GeV barrier. Okay, and it caused a sensation at the time, actually. Okay, it was, physics highlight of the year, and so I was very pleased about that. Not to mention, it led to my getting tenure at UCLA. So I was very pleased. More than that, I personally was happy because I felt I had not misrepresented my field by saying we can get GeV in meter. Okay, it's a lot of pressure because you said something like that. Okay, and so I was happy about it. Okay, so charge fraction, about 0.8% of the charge was accelerated, which was 25 picocoulomb, not one electron. Okay, a picocoulomb is 10 to the 6 electron. So 25 is more than 10 million electrons were accelerated. Okay, so the challenge was 1 electron by 1 GeV in 1 meter. My only regret in life has been I didn't ask him, if I do it, what do you give me? Okay, because he forgot, he pretended as if he never said it. Okay, but to his credit, after we did the next few experiments, he did write to me, and he did write a paper, actually, in which he mentioned that possibly the field of accelerator physics has reached saturation, is dead, and unless something like plasma accelerators comes along, we're not going to continue. Okay, so that I thought was very big of him. Okay, so this is the big result. This is really the big result. Okay, once we broke the GeV barrier, the slack physicists became greedy. Okay, they said, we will increase the energy of the slack linac. Instead of 20 GeV, we'll push it to 47 GeV. When they want to do something, they can do something fast. From 20 GeV to 47 GeV, they made the changes necessary within 2 months. The entire lab just went to work at it. Okay, although the main reason for the 20 GeV was the slack linac was a BB bar factory, B bosons, and B bar meaning they're antiparticle, BB bar factory. Okay, they actually stopped that work, changed the accelerator to 47 GeV within 2 months. Within 2 months, built the beamline for an experiment that could be plasma experiment that could be carried out. And here it is. We put a meter-long plasma source instead of a 10 centimeter long little lithium source, a meter-long plasma source. And we concluded that within 87 centimeters or 85 centimeters, okay, here is the electron beam at 42 GeV, I'm not 47 GeV, 42 GeV, and particles in the tail were accelerated out to more than 85 GeV. Okay, so if you do that at slack, to accelerate particles from 0 to 42 GeV, it took them 3 kilometers long accelerator, 3 kilometers long. That's how long the slack accelerator is. And the particles were taken from 42 GeV to 85 in less than 1 meter. So if you like, the claim that you could accelerate particles at 1,000 times the rate than you could with RF was fulfilled. And this was published. I was very happy when CERN Courier carried it. Of course, Nature was published in Nature. Okay, CERN Courier carried it on the front cover and saying doubling the energy in a plasma wave. And to me, why was this? Because it was a vindication and recognition by a major particle physics lab, not in the United States, that something major had been done. Okay, and so that I was very happy about that. Let's continue. All right, at about the same time, okay, this report, Building for Discovery, which is written by the National Academy of Sciences, came out. And in that accelerator, for the first time, oh no, this is actually Building for Discovery is a P5 report. P5, for those of you who don't know, stands for, let me get that right, Particle Physics Project Prioritization Panel. That means in the United States, although the Department of Energy gives money, okay, that money is given by consensus. Okay, so there is a community of particle physicists that decide what facility should we build next. Okay, and it's rare that the Department of Energy will go against it. Okay, they follow these reports. Okay, and that for the first time after this paper came out, this P5 committee report for the first time said a primary goal, therefore, is the ability to build the future generation accelerators at dramatically lower cost. That means high gradient. Okay, for electron-positron collider, the primary goals are improving the accelerating gradient. That means, only plasmas can do it. Okay, and lowering the power consumption. So it has to be efficient. Okay, at the same time, the National Academy of Sciences, this is at the turn of the century, about year 2000. National Academy of Sciences released a report called Engineering of Grand Challenges for the 21st Century. It's really a forward-looking document. It says, what are the grand challenges in engineering for the entire century? So number one, guess what? You guessed it, is producing economical fusion power. Okay, because our game is up as a society unless somehow power becomes cheap, affordable, right? No, so that's number one. Number two, making solar power, a reality is related to number one. Okay, and number three, they were so far ahead. I actually laughed at it. Okay, that is realizing artificial intelligence. Okay, in year 2000. Okay, and so, but one of them was engineering the tools of discovery. They said, none of this is going to happen if we don't have the tools needed to do the science. Okay, and one of them, then they basically said one of the tools of discovery was accelerator physics, I was really surprised actually, because I had nothing to do with it. Okay, they said in the 21st century, engineers will be able to devise smaller, cheaper, but more powerful atom smashers. They were engineers, right? They still kept on saying atom smashers. They didn't even know they don't smash atoms anymore. Okay, atom smashers, enabling physicists to explore realms beyond the current technology. But the report is so powerful that it had influence on the engineering community and funding bodies. Okay, all right, let's move on. Okay, I'll skip that. Okay, all right. So the first thing was, okay, all right, you showed doubling of the energy, but can you actually accelerate a bunch of particles, a second beam of particles, to high energy at a high gradient with a narrow energy spread? Why narrow energy spread? Because eventually you have to focus these beams down to very small spot size and collide them against each other. And to focus them down at one spot size requires you to have narrow energy spread. Otherwise, you get chromatic aberration. Just like if a laser beam had, a supercontinuum is very difficult to focus down, okay, except by using complex optics. Okay, so same thing here. So we did an experiment. This was also in front cover of Nature. You can say it says full speed ahead. Basically, we sent one beam to produce a wake. We put a second beam, okay, at the same energy, okay, and accelerated it. And this is the result. It shows that both beams initially had the same energy, about 20 GeV, and the second beam has now been accelerated by 9 GeV in 1 meter. Okay, so that is the world record stands today, even now, 9 GeV in 1 meter. Okay, and large number of particles. So energy spread was less than 5%, and 25% of the energy that was transferred from the dry beam into the wake had been extracted by the trailing beam. So significant amount of energy was extracted, not the maximum, but significant amount. And that's still the world record. Okay, so that's about electron. What about positrons? You might ask. Well, positron story is a little bit different. If you send a positron beam to the plasma, instead of pushing the plasma electrons out, positrons suck the plasma electrons in. Okay, and of course, the positrons, a relativistic positron beam is also very heavy particle. Nothing happens to them. Okay, but as the electron beam, plasma electrons are sucked in. They're sucked in from different radii, so they arrive on axis at different points at different times, and then they overshoot and form a wake. Okay, so as a result, the field is always a little nonlinear. It's not exactly sinusoidal. That's the accelerating field in green and focusing field in blue, and the focusing field is nonlinear. And as a result, an initial positron beam, which looked like that, okay, by the plasma, it is focused by the focusing field, but because the focusing field is nonlinear, there is a large halo around it. Okay, the halo production. This is the characteristic of nonlinear wakes. Okay, so how do you get around it? Oh, this shows also positron acceleration within physical review letters. Interesting story behind this is, this is the first time we saw positron acceleration by a plasma wake. I said, wow, this is fantastic. I'll submit it to Nature. Okay, wrote a paper to Nature. Nature said, you just showed electron beam acceleration. We put it on the cover. What more do you want? I think you publish it somewhere else. So we had to publish it in physical review letters. Of course, they accepted it right away. Then Nature had to eat crow and write a news and reviews special report that an important piece of work was published in physical review letters on positron acceleration by plasma. So I felt somewhat relieved by that. Okay, then we took an intense positron beam sent to a plasma, produced a nonlinear wake, and accelerated the back half of the beam to many GeVs in a meter, and there it is, basically. Okay, so basically the front half of the beam sucked in the plasma electrons, but some of the plasma electrons that came from near the axis were trapped by the back of the beam. They were sucked in, and they were focused to back of the beam, which became so dense that although the positrons were heavy in the back half of the beam, they felt the focusing force and they were confined. They came in towards the axis. and they were accelerated, and there it is, and they were accelerated in a narrow energy spread bunch, as if it was a separate bunch, by many GeVs, about 4 or 5 GeVs in 1 meter, and this was published also in Nature. So Nature kind of corrected themselves actually. So I'm very happy about that. Okay, so at about the same time when this two happened, Physics Today said, called me up and said, would you write a paper on plasma acceleration? I said, sure. So Tom Katsulas and I wrote a paper in Physics Today in which we proposed that today, meaning at that time, 2005 or something, 2006, okay, we could build a plasma collider at SLAC LINAC, okay, at SLAC, by placing a plasma, oh, sorry. I think this is important to kind of see. By placing 2 plasma sections, so one here and one here, okay, just before the collision point of the plasma of the SLAC collider, one that accelerates electrons, so that each section will have 2 beams, one a drive beam that produces a wake, one a trailing beam that is accelerated by a wake, and of course for conservation of energy, the trailing bunch has to contain fewer than half the charge of the drive bunch. Okay, because the energy is going from drive to trailing, and if you're going to double the energy of the trailing bunch, it has to have half the number of particles, right? So and we call this the afterburner. And why is it afterburner? You guys maybe know it, but I didn't know it. Okay, afterburner is actually a thing. Afterburner is what a jet engine, a fighter jet does when it suddenly makes maneuvers. Okay, here it is. So I took a picture. I don't know, there are many pictures of US Air Force planes, but I didn't want to do that. Okay, there's a NASA plane, and basically it's chasing a spacecraft re-entering. And so suddenly it has to catch up with the spacecraft, okay? So suddenly it has to go vertically up and catch up with the spacecraft. And so to produce the extra thrust, what it does is it uses the exhaust, which only partially burns the fuel, and injects super pure gasoline. Okay, and so suddenly it explodes and goes into a hydrodynamic instability called a wake. Okay, and there it is. You can see it just like our wake. Okay, it goes bunch of bubbles, right? Okay, and it's called an afterburner. So we call it the plasma afterburner. Okay, that is the genesis of the term plasma afterburner. Okay, now, unfortunately, SLAC at the same time decided to change from high energy physics into an X-ray free electron laser. Okay, so they changed their entire lab from high energy physics lab to photonics lab. Okay, and the demand was so great from the community for coherent X-rays that there was no stopping it. It was like a juggernaut, coming at you. Okay, and so we were rolled over. Okay, that was it. Okay, so where are we today? Well, the red ones, basically red points here, show where the laser-driven plasma accelerators are. Okay, and by here now we are at about multi-GeV at Lawrence Berkeley Lab, and the blue curves are the points our experiments, and our experiments have basically produced a maximum energy gain of 43 GeV. Okay, and basically the slope of this curve has to be steeper than this curve, right? If there's any chance that this curve is going to cross this curve. Okay, and I must admit that these are machines doing physics. These are experiments. And it can't be experiments, it has to be machines. But it's not as bad as you think. These experiments are done at 1 hertz, and every morning at 8 o'clock at SLAC, you have to go to a meeting like this, a public meeting, in which the Nobel Prize winners sitting in the front and, very senior people, just like this, okay? Senior people and sitting, and you have to give a talk, okay? Students and postdocs who've been working all night, give a talk, like what happened in the last 24 hours, okay? And if you say, we got 10 GeV result, you can't just show one piece of paper. You have to show, well, 200 shots, all the shots that can fit on a view graph and result. And they better look the same, okay? So, in other words, the degree of, when they say proof or something worked in using accelerator physics is different than in laser plasma interaction physics, okay? So I don't feel too bad. I think technology and also learned something else being working in the middle of Silicon Valley. Engineers are awfully clever. Okay, they will perfect their machines to be reproducible, so that the spatial jitter is varied and temporal jitter is varied and so on. Okay, so accelerator-based physics in 21st century, is there any hope for it? Well, here it is, basically. I like this, I like this cartoon. This young lady is being courted by several men, okay? And she kind of has to finally turn around and say, sorry, I know you got charm, okay? And there's a pun on the word charm to work out for, okay? But I'm really into brains. And notice the brains is for the membranes of string theory. Okay, so the recent 2024 particle physics P5 report suggests that a 10 TeV center of mass electron positron collider, which is really equivalent to about 100 TeV positron anti-positron collider. And it really would have to be positron anti-positron collider for the best results. But anyhow, I won't go there. Will be needed this century to keep the particle physics, accelerator-based particle physics vibrant. Okay, so this is I mean, remember, we are at equivalent of at LHC about 150 GeV center of mass, because we found the Higgs particle. Okay, but we haven't found any other Higgs particles. There may be more Higgs particles. We haven't made any kind of careful, systematic measurements of the properties of the Higgs. Okay, for that we need much higher energy. Okay, so in the United States, at least I should just tell you what things are, what is going on. Okay, just like the particle physics project prioritization panel P5, okay, they produced a community and asked them to come up with a report what was needed for making a 1 TeV plasma-based collider. Okay, so I just put it, here it is. The report is here. The Advanced Accelerator Development Strategy Report. This is from our positron acceleration paper, and much of the report is taken from my Scientific American article. So it had a huge impact, and it basically they basically, this is summary of it. Can critical physics issues for a multi-stage electron-positron collider be quantified via experiments and/or simulation in the next decade? And the paper, next decade is running out, because this thing came out in 2017. By 2027, and there's no forgiveness, Corona Ferona. Okay, they're like, they don't care. They mean 2027, because luckily, where does that come from? It comes from LHC's, the Large Hadron Colliders, plans for the decadal plans for doing science. Okay, but they've been affected by Corona. So I'm not, in reality, I think it is delayed by a couple of years. Okay, so it's not 2027, it's probably 2029. But the decade is going fast. Okay, now, can the remaining critical issue be resolved by 2032? Well, okay, it will be 2034, 2035. Okay, but there are a lot of issues. What are they? Issues are, the main issue is acceleration of polarized electron and positron beams, because physicists would like polarized beams, because collisions between polarized beams preferentially, as I understand it, preferentially give higher weight to certain outcomes, certain pathways, than if the beams were unpolarized. Okay, so imagine that if the interaction between particles and bosons has 10 different pathways, okay, then that all these collisions have to be analyzed to find the one that you want. Okay, but if 9 of those can be discounted because they are dependent on spin, then you have less data to analyze, and you can concentrate on that. Okay, so they basically wanted, essentially, by 2032, remaining problems to be solved, at least theoretically, that means that there's no showstopper. electrons and positrons can be accelerated, and spin polarized beams can be produced in situ and accelerated in the amount that is necessary to produce the luminosities that you need. Okay, that's number one. And then they're basically saying, well, T1 TeV, but we need an intermediary demonstration of 100 GeV collider, electron positron plasma collider. And this and somebody else has to fund it. And so, in other words, you have to come up with an application for a plasma collider. So application for a plasma collider is the 5th generation light source or an X-ray free electron laser that is compact and cheaper. Okay, and so if you could do all this and propose it, then can the community come up with a CDR, conceptual design report, for a 1 TeV plasma-based collider by 2035? Well, maybe 2037, but it's going fast. Next 12 years or so. Okay, so I've been asked to write a letter. I asked a paper by Nature Physics. This will come out, I guess, hopefully sometime soon. That shows what a conceptual electron-positron plasma-based collider will look like. But it looks like basically a RF linear collider where instead of RF sections accelerating particles, it's plasma sections accelerating particles. Okay, but the beams, the good beams that you need, low emittance, high intensity, high charge beams that are spin polarized, still come from traditional accelerators, because we don't know today how to do it. Okay, let's move on. Okay, this shows intermediate parameters of a TeV collider. I'm not going to go through all of them. Particle physicists always show that. It used to drive me crazy when somebody showed, big tables of numbers like this. Like, really, you really think people are going to see it and remember this? They're not, right? So I want to. But it's just showing to show you that it can be done. Okay. In the meantime, okay, how do we produce? What is the next big challenge for plasma accelerators? The demonstration of all the necessary parameters for a single stage of a plasma collider. This has been done for electron beam, using particle simulations. Okay, and this is the experiment that we are doing right now at SLAC, and it basically shows a dry bunch here and a trailing bunch, and it's going to the plasma, and nothing seems to be changing, but this simulation is running. This goes to show how stable this plasma accelerator is, and basically it decelerates the beam, the dry beam, which is here in the front. I'll run this again. Okay. Okay, here we go. Watch this. Both beams started at 10 GeV here, 10 GeV, and dry beam is losing energy, trailing beam is gaining energy, and let's see what happens to it. The dry beam is losing energy, and as the dry beam runs out of gas in the middle, most of the particles have lost energy. Okay, this is going to go down to 0, and this one is going to go down to more than 10 GeV or 20 GeV, 10 GeV actually. Okay. And so it's going to energy doubling of the beam. So it can be done, and it's an experiment that's going on. We have lots of results actually on this already, preliminary results, but I'm not prepared to actually without critical discussion among the collaborators to show them to you. Okay, and we also show that the emittance can be preserved of the beam, which is very important. Here's the emittance of the beam, and here is a beam that is matched to make sure that the emittance does not increase. Continue. Okay, now very quickly, what about the interim application? Well, you can see producing a collider is a grand challenge for the century, and many things are not shown yet. Okay, just because we show the beam parameters needed for one stage doesn't mean we can put the stages serially together and produce a beam without loss of charge. Okay, because even if we lose 5% of the charge per stage, if we have 20 stages, all the charge is gone. Okay, so we can't afford to lose any charge. And at the moment, we can only transport about, let me tell you what, 70% of the charge in one stage. So we lose 30% of the charge in one stage. So in three stages, all the charge is gone, right? So we don't know. But if you look at the fifth generation light source, it only needs one stage. And we know how to do this for electrons because we will just do it for electrons. We don't need to do positrons. Okay, we know we only need about 1 GeV dry beams. We need only 10 picocoulombs of charge in the accelerator bunch. Okay, we need a single stage. We need a high beam brightness. We've shown that we can do it in particle simulation, and our new results show high beam brightness. Our beam brightness is as good as beam brightness of the LCLS2 beam. Okay, the second generation free electron laser. Okay, we have to show nanometer emittance. Well, we're not quite at nanometer emittance, but we had micron emittance, which is really very good. And kilohertz rep rate, we're at 10 hertz rep rate. So we're close. Okay, so here it kind of says that we don't know how to do kilohertz rep rate for sure. Okay, now why is that important? A second generation light source, because undoubtedly, in my mind, and I'm sure you know, probably all know this, that next century is going to be a century of biology. Okay, why? Because we all getting older. We all going to get genetically related diseases, cancers and other diseases, that inherited diseases like diabetes and so on. Okay, and so what does this show? This shows the latest Nobel Prize, by the way, not latest, not this year, a few years ago, given to Ramakrishnan, I think it is, of MRI. Yeah, okay, for decoding the structure of the ribosome, which is in every nucleus responsible for production of proteins. It's a protein generation and enzyme generation engine. Okay, and you can see this is a complicated damn thing. Okay, I mean, I'm amazed that somebody resolved this, and this is a mathematical problem actually, because you look at the X-ray diffraction pattern, just like Watson and Crick, okay, looked at the diffraction pattern from a double helix of a human DNA molecule, okay, and why was that possible? Because somebody managed to crystallize the human DNA into a crystal structure and take a diffraction pattern of it. Well, it turned out to be very simple, right? If you have a regular double helical structure, you get a particular pattern. But look at this molecule. I mean, this molecule, I mean, how do you do it? No, even if you had X-ray diffraction pattern, unless you had it from every conceivable angle, so you get a tomograph of it, and then you could predict from looking at the diffraction pattern what must be a unique solution. You're looking for a unique solution for a diffraction pattern. Okay, what the unique solution is, you cannot do it. So you can see why it produced a Nobel Prize, right? But the main breakthrough is you need now there's a major breakthrough, that is, instead of using a synchrotron to produce, first of all, you have to crystallize the ribosome. You have to take this ribosome molecule, which is nanograms of it, is not oriented the same way. So it's kind of randomly kind of falls down, is encapsulated in some liquid droplet. Okay, and you take these X-ray patterns and you try to deduce from a zillion patterns what unique solution is. To me, it is amazing that they got this. Okay, but now people have got X-ray free electron laser, and with LCLS2 in one shot, you won't need, in a few shots. So they're working on producing, aligning the crystalline molecule encapsulated in a liquid droplet in a particular way. So in a few shots, you can get, you can get diffraction pattern and get a three-dimensional model of it. Okay. Now, why is it important? Because there are 100,000 proteins in human body, and we need to understand their structure. Only a handful of proteins have been decoded. They have been decoded. Okay. So, for example, the proteins that exist in the eye, rhodopsin or something. Rhodopsin. Yeah. Okay. Thank you. Okay, has been decoded. Okay, so few have been decoded, but others haven't. Same thing with enzymes. What are enzymes? Enzymes are proteins that are catalysts. So think of catalysts. So they take part in the interaction, chemical interaction, but they act as an intermediary. Okay, so there are 75,000 proteins that are enzymes in human cell, human body, and there are 25,000 genes in each cell. Well, you don't have to, that doesn't mean anything. There are 25,000 genes, okay, that need to be decoded, okay? So the human genome has been decoded, okay? Human genetic map has been made, okay? Genes have been generally identified, but not precise workings of the gene. Okay, I perhaps didn't explain this properly, but anyhow. So there's a lot more work to do. And that is why X-ray free electron lasers are important. And it is going to be, I mean, I was on the scientific advisory committee for SLAC, and let me tell you, it is brutal for the poor director, because the committee sits there and say, okay, you've been at it for 10 years. Where's the Nobel Prize? And the guy resigned in the end. He said, I can't stand this. Okay, and he was really well known. I think either physical chemist or microbiology person at Stanford University. Okay, so what are the near-term applications of plasma accelerators? Very quickly, radiography of biological and high-energy density targets using synchrotron-like radiation. It's called betatron radiation. And the second one is radiation therapy using very high-energy electrons, rather than photons. Okay, so I like to show this because directional but incoherent, intense beams were observed first by a student of mine who said, Chan, I would like to, everybody calls me Chan, okay, even students. So he said, Chan, I would like to propose that for my PhD, I look for synchrotron-like radiation. At that time, we didn't call it betatron radiation, synchrotron-like radiation. Okay, that comes about because of the motion of the accelerating electrons in the electric field, transverse electric field of the ions. Okay, and I said, okay, if you want to do that, it's fine with me. The committee, the PhD committee said, are you crazy? I mean, this guy has to discover something to get a PhD. And what happens if it doesn't work? I said, well, he really wants to do it, and he's worked out everything out. And sure enough, the first experiment he did, he saw it. Okay, so that's called a robust experiment. This is the synchrotron radiation pattern produced by the beam after it is deflected down and dumped. And this one is the betatron radiation. Oh, sorry. Betatron radiation, which is 20 meters away, comes across as a small spot, intense small spot. Okay, and this is then simulation. This is a nice graphic produced by someone at Livermore. Okay, that Felicia gave me. Okay, now what about, so I'm saying that this radiation is so intense and so directional that it could be used for radiography, for some preliminary analysis. So I think it is, and I think same thing with a petawatt laser, the betatron radiation application could be developed, using the laser source that you will have. Now, what about very high energy electrons? Well, it turns out that electrons, there's some advantage in using electrons instead of photons for cancer therapy. Okay, this is a paper that we wrote with, but this view graph is courtesy of Victor Marca, who gave this to me. And it basically shows how 20 MeV electrons deposit their energy inside a human body, okay, yeah, compared with photons or compared with high energy protons, which are 230 MeV. Protons are the best because they have a Bragg peak. Okay, so they slow down continuously, and then suddenly at the end they deposit almost all their energy. Okay, and so there's the energy deposited by proton beam. This is the energy deposited by electron beam, which is more uniform at least. So if the tumor was not deep rooted but closer, okay, you might want to use an electron beam. And this shows basically treatment of a human prostate, which is deep-seated actually, which is about 4 to 6 inches seated from from the nearest closest tissue and irradiated from several different angles. So this is very high energy electron beam. This is done with protons at 6 MeV, and this is done, and this is this is photons with 6 MeV, and this is the difference. And you can see that there is a significant difference with photons at 6 MeV. You get significant damage to surrounding tissue. Okay. All right, so we're almost finished. Okay, so what is my conclusion? Okay, my conclusion basically is that developing plasma accelerators that will disrupt an established technology is a long-term, lifetime endeavor. I've been at it for almost 4 decades. Okay, and Maury Tigner, who was actually at the head of the SSC at the time, he said, all physics, the measure long-term physics is to be measured in a human lifetime. Because if it's not brought to fruition, the next generation loses interest, or they want to make their own name. They choose their own problems. The problems change, human priorities change. And he was right. Wise man, he was right. At the time, I didn't think so. But okay, now, what have I learned from this? That really what you need is a team that has diverse expertise. I did not have expertise when I started. First 2 decades were wasted because I tried to learn the language of accelerator physicists. Okay, and accelerator physicists tried to learn what the hell plasma physicists were talking about. Okay, 2 decades were lost. Many accelerator physicists came and warned me, said, Chan, don't say crazy things. Okay, I mean, don't say that you're going to, to them, it was inconceivable that you could accelerate at GeV per meter, let alone 20 GeV per meter. Okay, it was inconceivable. Okay, so you need a team that has diverse expertise. You need bright young people eager to make their mark, and good leadership is, who can argue with that? Good leadership is essential to success. Long-term funding and access to facilities is essential. No, not everybody is going to have a petawatt laser. Okay, so you're going to have to attract people who are interested, who are bright, and who have something to bring to the table. Okay, not everybody is going to have a slackline act. It's $1 billion machine, $1 billion machine. Okay, so today, nobody would think of building a slackline act, right? So then I firmly believe, and this is what I learned through all the new physics we did, that it's important to have goals to judge the progress, but we must also have the freedom to pursue unexpected results or avenues as they turn up. Okay, so Betatron radiation, for example, direct laser acceleration. There were many new things that came along, new discoveries that came along the way that were deemed very high quality in the physics community. And I'm grateful for that. Okay. And finally, I think my advice to students who are here, okay, openly share your ideas. Okay, don't try to hide it. It's not like, secret. Don't be secretive. Just openly share your ideas. Just do it first. Okay, so don't worry about competition. Ask advice. Talk to everyone. I personally talk openly to everyone. Okay, and adopt best practices. And it's not, I cannot advise you what that means. Okay, but you only have to look at airports, railway stations, roads, and you kind of say, why is such and such a country, I won't mention any name, not United States, why are their roads clearly better? Okay, and function much more much more smoothly for traffic. Why are the airports much better for passengers? Why is it a much better experience for passengers? So best practices, as one US Supreme Court judge famously said, when a case involving pornography came in front of him. Okay, and the lawyers started arguing, what is pornography? This is not pornography, this is art. And the judge said, pornography is obvious. You know it when you see it. And so that's what adopting best practices is all about. You know it when you see it. So adopt best practices. Okay, thank you. That's it. Sorry, I've gone over quite a bit. I think, maybe that will be better so everyone can hear it.
Hi, Chan. Thank you for the inspiring talk. Basically, I have 2 questions. You have covered plasma wake field and laser wake field separately, and there is also this hybrid wake field where the electrons from generates plasma wake field in the second cell when you take 2 stages. There are some instabilities that comes into play, like BNS instability for plasma wake field and electron housing instability that comes up. In order to obviously get low mittance beams, we need to address these instabilities. So could you please touch upon how to mitigate these instabilities?
Of course. This is a specialist question. Okay, the question was about if there is any misalignment between the driver, either a laser beam or an electron beam that's producing the wake, and the trailing beam, that's the second beam that is being accelerated by the wake. If there's some misalignment, for example, then that misalignment tends to grow, okay? And that as it misalignment grows, it produces an increase in the emittance of the beam, meaning divergence of the beam. Well, if the divergence of the beam increases, then it's difficult to focus it because your focus is set at a certain distance, at a certain focusing strength. Okay, everybody will understand that, right? I mean, I think I'm trying to make it simple. And so if there's an instability that increases emittance, that increases the focal spot size and thereby the emittance of the collision bunches, colliding bunches. And what does emittance mean? It increases emittance and therefore decreases the luminosity. What does luminosity mean? Luminosity is basically, luminosity times the cross section is the number of events per second. Okay, so if it number of events per second goes down, then hey, you'll have to wait all your lifetime to see a, the supersymmetric particle. I say supersymmetric only for the reason, that's what we're looking for, okay? Or another Higgs particle, okay? Another version of the Higgs particle, not on the Higgs particle, okay? So the point is, what do we do about this, okay? So there are several solutions. One is that basically what you have to do is you have to produce a longitudinally varying focusing force. So the front of the beam sees a different focusing force than the back of the beam, but correlated. What that does is it changes the betatron wavelength of oscillation about the transverse thing, and that produces a dephasing such that the emittance grows by a small amount, but then thereafter it reaches a stable quantity and beam propagates. Okay, so you work backwards and you say, well, knowing that emittance is going to increase, I'm going to fold that into the design and build what kind of longitudinal focusing, non-uniform focusing field I need. Okay, and you build it in the design. And you can do that by having asymmetric beam, dry beam, and you probably well know, and the particle physicists will certainly know, that there are some advantages in focusing asymmetric beams. Okay, in fact, people want asymmetric beams. Okay, so I won't go into why. Okay, this is a very specialized subject. Okay, so by having a specialized beam, a asymmetric bunch, therefore asymmetric wake, you can also get rid of or reduce or get rid of the transverse beam breakup instability. Okay, you mentioned beam breakup. It's called Hosing instability in plasma physics, or beam Hosing instability. So there are solutions. Okay, that's why I didn't mention. Okay.
So, of late, like in last 2 years, there is this concept to generate spin polarized electrons, like you were talking about. One of the group in DESI is working on, you can take multiphoton ionized spin polarized electrons from argon gas and then inject into the laser wake field and see if the spin is preserved or not. Is there a similar work in the plasma wake field acceleration as well? Is the spin preserved, spin is not preserved? What affects the spin?
Actually, we ourselves published a paper on in situ, that means within the wake itself, by using ionization process, producing spin polarized electron beam and accelerating it. Okay, so I think that problem has been solved. The problem is acceleration of spin polarized positrons, because the only way at the moment of producing positrons is from high energy electrons hitting a high Z target. Okay, so you convert electrons into virtual photons or real photons, which then decay into electron-positron pair, and then you collect positrons, and you have originally spin polarized electrons, so that the spin polarization is conserved, okay, or carried through. I mean, there's some degradation, quite a lot of degradation actually, but at least you get partially spin polarized positron pair. And the remaining, and I challenge all of you, please, we need help. Okay, if you think of a brilliant idea of generating spin polarized positron beams, let me know, because it is the most outstanding problem.
In the actually, sorry, can I ask? In the similar line, there is this Brightwheeler process where a photon hits a lead metal to generate E plus E minus pair. Can we generate a positron, a spin polarized electron from a wake field and hit a lead metal, and photon generated from this interaction interacts with the lead nucleus to generate E plus E minus pair? Is there any connection from spin polarized electron to spin polarized positron?
Well, I think you're very perceptive, and there are many ways of producing a spin polarized positron, but it will be a spin polarized positron. We need 10 to the 10th per shot at 10 kilohertz. Okay, the requirements are so severe on a future collider to get the luminosity that you need that I certainly don't know it. You know, all I urge you to do is, when my paper in Nature Physics comes out, is look at that table and see whether you can come up with an idea that will produce that many spin polarized positron. Okay, because really we need help.
Yeah, nice lecture. You are talking about nonlinear waves. Now, do you have any specific model for this nonlinearity, like this higher order powers of the field, or this some saturation type or anything? Any specific model of nonlinearity?
I'm sorry, I didn't fully answer the question.
Is there any specific model for the nonlinearity
Right.
of the plasma waves?
Right. Okay, so for the longest time, the most outstanding question was a model for nonlinear wake formation by a positron beam. But now we have an answer. So that goes to show young people are very smart, actually. Okay, and so somebody they're going to make their career, but that's it. You know, you only need one good idea and that is accepted by the community. But there is a solution. But what we don't know is how to produce now. We got to the next level, how to produce a spin polarized positron. So there's a model, yes. There's a model. It's a heuristic model. That means it's not mathematically self-consistent and sound. And you know, I think many of you might be purist theorists, will kind of discount heuristic models right away. But heuristic models are actually very useful because if they are supported by particle in cell core simulations that have no assumptions, okay, only electromagnetic force, that's all you need, interaction with charged particles, then it must be right. Okay, and these particles in cell core simulations have been validated by numerous experiments that we have every reason to believe that, you know, they're good. Yeah.
Thank you.
Okay.
Any other questions you have? Do you have a question? Okay, I thought you have a question. I have a question actually. This 1 kilohertz, you know, 500, not 500 meters, less than that you had put for the kilohertz
Repetition.
500, 1 GeV beam.
Right.
So now if I understand right, you need a conventional drive beam to further accelerate with the plasma wave.
Right.
And 1 GeV accelerator drive beam itself will be kilometers long, or at least 1 kilometer long. So,
But they exist.
but they do exist. So but you still need to make that into a compact accelerator, right?
Yes.
So what is the proposition?
The proposition is the Facet 2 facility at SLAC already produces 10 GeV beams at the necessary peak current at 10 hertz, not at 1 kilohertz, but SLAC beam can be upgraded to be at 120 hertz. Okay, so you might say, well, there's a big difference between 120 hertz and 1 kilohertz or 10 kilohertz. But the LCLS2 beam is going at, I think, 1 megahertz. Okay,
Yes.
eventually,
Yeah.
well, not right now, it's not going at 1 megahertz, but it will go at 1 megahertz. So if we can show that using the facet 2 beam, we can do experiments at, let's say, 100 hertz. Okay, that will be a huge argument for saying, give us the LCLS 2 beam and let us put a plasma at the back in the front of it, and let's see whether we can operate at a megahertz. That is the long-term strategy. Okay, you have to do that.
No, and other question I have is for those of us who don't have access to LCLS or SLAC,
Right.
if you want to do interesting experiments of this kind,
Right.
is there any sort of a smallest version of 10 MeV LINAC or something that you can do some basic physics with this?
I'm sure you can. Okay. I would say that there is a lot more physics you can do with the laser unit.
Of course.
Okay, I mean a lot. Okay, and I myself have many ideas. Okay, and I actually could have given a talk here, but I think I don't. I think it would have been. This is a more like a colloquium talk, useful for a student. That is so specialized in plasma physics that nobody would be interested except a few people. Okay, so but maybe we can talk if those
Yeah.
people who are interested in knowing what can be done with what I think can be done with a laser like that. I think we can talk about it.
Okay, maybe we can have that tomorrow.
Yeah.
For a,
We can do it tomorrow for a small group, number of
for a
people.
small group, yeah. No, yeah, the super bunch, then it goes to super bunching, right? I mean, any other questions? If not, let's thank Chan for a fantastic inspirational talk.